Hi, I'm Jack Buffington for robotbrigade.com. In this video, I'm going to take the two topics that I discussed in my previous two videos and combine them together into something that's useful for a robot. Specifically, I'm going to be allowing a robot to figure out its position and heading based on video data. And so let's take a look at the setup that I have. I first needed to get some video, and I'll say that this is a demo and not actually implemented on a robot. So I actually recorded the video on my cell phone. And instead of having a fixed lens, I actually ended up getting a little thing. I got it off Amazon for like 20 bucks. It clips on, and this gives me a fisheye lens. It said it was over 180 degrees, but it's actually maybe 140 degrees field of view, something like that. And so I clipped this onto my phone, and it gave me the view that you see on the right here. And so the steps that I did to figure out the pose of the robot is to first record the video. That came with a few hurdles of its own. As it turns out that both of the two phones that I have image stabilization, and you can supposedly turn it off, but that isn't actually true. Though I did find that the selfie camera never has image stabilization, and so I used the front camera instead of the back. So I recorded my video and I brought it into the computer. And I ran that through a blob finder. So this blob finder was taking the video and converting the images into hue, saturation, and value. Then it was doing window compares for each of the three colors it was looking for. And actually I did all four. And then I was outputting to a text file where the centroids were located for each color. Now, because I was finding my centroid locations in image coordinates, I needed to adjust this to coordinates that were centered around the optical center of the lens. And so you'll see a circle that represents the edges of the fisheye. And I wrote another program that I manually drew a circle over there, and I kept adjusting things until the circle overlaid the actual imagery of the lens perfectly, and then I recorded what those were. I passed the center coordinate to another program that subtracted that away from the image coordinates, so it gave me the coordinate of 0, 0 right at the optical center of the lens. And that was important because I need that to calculate the angles. If I have it all in image coordinates, I only get, the first quadrant. All of my angles would be in the first quadrant, which is not what I want. Now that program saved things out again as a text file, and I passed that into the algorithm that I showed in my first video, where I found 3 points and computed the position and heading from them. And finally, I plotted the results. So here's an example. I did my initials JB, and my setup was actually that I produced some circles that I had stuck to my ceiling. In the past, when I've done things like this, I have used gouache paints because they're nice and vivid. But this time it appeared that all of my gouaches had dried up because I hadn't touched them in years. And so I just used some acrylic paints that were in my son's paint set. And so they aren't terribly vivid, but they did the trick. And you can see over here that I did successfully trace my name, though we do see right here and here that there were some points that it was getting a bad result. Here I did a triangle, and you can see I'm getting more bad results in this one. And specifically over here on the right-hand side, it was starting to lose this blue dot right here. As it got towards the edge of the lens, the hue was shifting and it was causing problems. It's not too bad, but let's take a look at this one. This one is clearly a square, right? Except that we're missing the whole side of this, and that's because, again, the blue was getting too close to the edge, the hue was shifting, it was getting small, and it just was getting bad results. So let's look into why and how I corrected it. So this video is the orange, the output of what I did after I did my window compare. And so you can see the orange circle right here is very clear, but we're catching some fringes on the edges of the lens, and like I think this is my mantle right here. This is probably due to image compression is my guess, though the edge of the lens may be also contributing some with chromatic shift. But overall, throughout that, you can see the orange pretty well. Now here's my blue, and you can see blue wasn't doing as well, but it's getting good blobs through here. And then as it gets towards the edge of the lens, it just basically disappears. And so now it is matching to things over here, which is also some fringing on the edge of the lens. And I probably could have fixed this by specifying different parameters for the window compare that I was doing, but I ended up taking another approach that made it a little bit more robust. So let's look at the output of, I think this is hue. Yes, this one's what we get when we look at the hue of things. So black tended to be towards red, and just the way the OpenCV works, it makes the highest hue be 180. It does it in degrees for whatever reason. Every other algorithm I've ever seen does it 0 to 255, but this is what OpenCV is doing. So, that's kind of interesting. You can see that where it doesn't have a whole lot of information, where it's really dark. Also, you can see my computer's running out of space. Anyway, where it doesn't have a whole lot of information, it's having difficulty computing the hue, because the hue is based on the ratios of, you get like, there's red, green, and blue, and you get the main, not quadrant, but trident. You figure that out, and then you look at the ratio. Let's say red's the brightest one, and you look at the ratio of blue and green, and that tells you how far you are away from red and in which direction. But if your values are like 1, 5, 3, which is basically black to our eyes, when you convert to hue, it can be all over the place. Likewise with saturation, you see a ton of noise over at the edges. And I'm not sure why it's so choppy here. Probably because I was running out of space on my computer when I was trying to record this. Again, saturation, I misstated it in my original video, in my previous video about blob finding. I don't know if you're watching this at a time before I have re-uploaded a new video correcting that, but in that video I misstated how saturation was calculated. It's very close, but it's been 5 years since I had written a RGB to HSV converter. The way that saturation is actually computed is it takes the maximum RGB value minus the minimum RGB value, all divided by the maximum. So again, when you are in a black region, you don't have much difference to go to, and so you could have, if it's like red, green, blue is 100, that could be fully saturated. And so that's why we're seeing tons of speckle over here. So you do have to be very careful of keying just on saturation. But in the end, that's actually what I did. So you can see that the dots on the ceiling are actually very saturated compared to the ceiling around them, with the exception of this one, but it's still good enough. Previously, I was searching the whole image and finding the largest blob. What I did instead was on my very first frame, I found the blobs, and then thereafter I used the centroid as a prior, and I searched in a small region around there for the blob, because it's not like it's just going to jump to some other place in the video unless you rotate really rapidly. So that did a very good job of finding the blobs now, and I ended up with, whoops, let's go there. There we go. I ended up with results like this, where I have no incorrect locations that it computed. So that's an algorithm that you could use to figure out your position and heading for a robot. I'm posting my code online, but you might want to just take that as an example and write it in C++, because I wrote this in Python. I just needed to get it together quickly for something else that I was doing, and not a YouTube video, but I figured I'd present it here anyway. Yeah, it works in Python. If you don't need to process it for every frame, it would be fine in a mobile robot, but I would never put it in there personally, just because I really like efficiency. So I tried to do this initially in C++, and I was having trouble getting OpenCV installed. And so because I was under a time crunch, I just switched over to Python. There's three things I wanted to touch on before I wrap up this video. And the first is that I said that this algorithm can produce a heading as well as the X and Y coordinates for the robot. I didn't show that here just because I didn't want to go through the trouble of producing a program to make an animation of which way it was headed as it was moving around its path. But I did build a simulator that produced simulated angles, and then I ran them through my algorithm, and it produced results that were identical to within numeric precision. So there'd be a few decimal places that are slightly different because of the floating point math, but otherwise it was the same answer. Which brings up another thing that is apparent if you run the simulation from my code, and that is that when you get directly underneath, or even around one of the landmarks that you're using, your results are going to become unstable, and that's because you can't determine a good angle from it. This is probably more true if you did the rotating columnator than with the camera, because you have so much resolution there that you should still be able to find a decent angle, but it will become unstable as you get close to underneath it. And that would be a time when it would be useful to use that fourth landmark that I didn't actually use in this video. If your algorithm switched over to using the 3 farthest away landmarks, then that would give you your best results. Finally, I just wanted to touch on one interesting thought that occurred to me while I was doing this. It was not possible with my setup, but if you used a fixed lens that you could characterize, and you knew exactly what angle each pixel was coming out at, then you could also determine the height of your camera, which would be kind of useful. And I suppose that if you threw an accelerometer in there and you could know your tilt as well, then you could get all 6 axes within a certain range where you could still see all enough landmarks to do your solve. So I hope you found that interesting. You know, I produce these things for you guys. So for robotbrigade.com, I'm Jack Buffington.